In this lesson, we are going to slow down one of the simplest ideas inside a decision tree. The question is, can one simple rule, based only on time spent on the website, separate sessions that are more likely to purchase from sessions that are less likely to purchase? That one rule tree is called a decision stump. It has a root, one split, and two leaves. Even though it is small, it contains the same ingredients used by larger decision trees: a feature, a threshold, a measure of impurity, and a score that tells us whether the split helped. The goal is not to memorize a formula first. The goal is to understand what the formula is measuring. We start with labeled examples. Each circle is one website session. Blue means the session ended in a purchase. Orange means it did not. At this moment, the circles are just a packed group. The model has not made a rule yet, and there is no time axis on screen. But each session already has two important pieces of information: a feature value, which is the number of minutes spent on the site, and a target label, which is the purchase outcome. That is the supervised learning setup. The algorithm is allowed to look at examples where the answer is already known, and it tries to find a rule that organizes future examples in a useful way. Now the same sessions are arranged by the feature the stump is allowed to use: time spent on the website, measured in minutes. Nothing about the examples has changed. We have simply put them on a number line. This matters because a threshold split is a cut on that number line. A threshold, or cutoff, says, sessions below this value go one way, and sessions at or above it go the other way. Notice the pattern is not perfectly clean. There are orange sessions at longer times and blue sessions at shorter times. That is normal. A useful decision tree split does not require perfect separation. It asks whether one side becomes more dominated by one outcome, and the other side becomes more dominated by the other outcome. A candidate split now appears at about 8.5 minutes. We call the threshold tau. Tau is just the cutoff value in the rule. The rule is, if the session time x is less than tau, send that session to the left leaf. Otherwise, if x is greater than or equal to tau, send it to the right leaf. The bottom groups show what the stump would produce from this one rule. The parent group of website sessions has been converted into two child leaves. Once the leaves exist, we can ask a new question: are these leaves cleaner than the original parent group? At this point, 8.5 minutes is not a winner. It is only one candidate we know how to score. Now watch the membership of the leaves. As tau moves, the line is not the only thing changing. Individual sessions cross from one leaf to the other. When tau is very low, only a small number of short sessions are sent left, and almost everything else goes right. When tau is very high, the opposite happens. The left leaf contains most of the data, and the right leaf becomes small. Between those extremes are many possible rules. This is why a decision tree algorithm does not simply trust a visual guess. It can try many candidate thresholds, often at positions between sorted observations, and score each one. The best split is the threshold that improves the leaves the most according to the chosen impurity measure. Here, the threshold control becomes part of the chart. That is a useful mental model. Tau is the adjustable parameter of this stump. Changing tau changes the question the tree asks. A lower tau means the right branch accepts more sessions. A higher tau means the left branch absorbs more sessions. The branch labels tell us exactly how the rule is applied. In the interactive widget, you can drag the threshold. In training code, the computer does the same idea systematically. It generates candidate cutoffs, computes a score for each cutoff, and keeps track of the best one. So the visual control is standing in for the search procedure used by the algorithm. The leaf panels now show two ideas we need before the formula: outcome mix and coverage. Outcome mix tells us whether a leaf is mostly blue, mostly orange, or still evenly mixed. A mostly one-color leaf is easier to interpret. If future sessions land there, the stump has a clearer majority outcome to use. Coverage tells us how much of the dataset the leaf contains. At this example threshold, the leaves are almost balanced in size. About half the sessions go left, and about half go right. That matters because a leaf can look very pure if it contains only a few unusual points. A good split should not only create cleaner groups, it should create cleaner groups that cover a meaningful share of the observations. Now we turn the visual idea of mixedness into a number, Gini impurity. For two outcomes, Gini is low when one outcome dominates the leaf. If a leaf were all blue or all orange, its impurity would be 0 because there is no mixture. Gini is highest when the leaf is close to 50-50 because a random session from that leaf gives the least certain majority signal. One common formula is 1 minus the sum of the squared class proportions. You do not need to derive it here. What matters is the behavior. Lower Gini means cleaner, higher Gini means more mixed. The parent group is close to maximally mixed, around 0.15. The two leaves at this threshold have lower Gini values, roughly 0.29 and 0.31, so this split has made both sides cleaner than the unsplit parent. When tau moves again, the Gini markers move too. That is because impurity is calculated from the sessions inside each leaf at that moment. A threshold near one edge may create one very small leaf and one leaf that still looks much like the parent. A threshold near the middle may create more balanced coverage, but the class mixtures might not be equally clean. The best threshold has to balance these effects. This is the key step that turns split selection into a numerical search. For each candidate tau, the algorithm asks, what are the left and right leaves, how mixed is each one, and how much data does each leaf represent? Once those pieces are known, the split can be scored. The layout now rearranges to make room for the calculation. The data has not changed, and the split rule has not changed. We are just organizing the bookkeeping. At the top is the parent distribution along time. Below it are the two leaves created by the threshold. On the sides are the quantities we need, each leaf's class mix, each leaf's coverage, and each leaf's Gini impurity. Those are the ingredients for split gain. Gain will compare impurity before the split with impurity after the split. If the after-split impurity is much lower, the threshold has done useful work. Now we can name the score the stump is trying to maximize, split gain. In words, gain asks, how much impurity did we remove by making this split? We start with the impurity of the parent node. Then we subtract the impurity that remains after the split. The important detail is that the after-split impurity is weighted. The left leaf's Gini is multiplied by the fraction of sessions that went left. The right leaf's Gini is multiplied by the fraction that went right. Then those weighted pieces are added together. Why weight them? Because a leaf with many sessions should affect the score more than a leaf with only a few sessions. Otherwise, a threshold could look good by carving out a tiny pure group while leaving almost everyone else mixed. So the formula is delta G of tau equals parent Gini minus weighted left, Gini minus weighted right Gini. Larger delta G means the split reduced more impurity overall. So far, we have focused on one candidate threshold, but training a decision stump means comparing many of them. The gain curve is the score sheet for that comparison. Along the horizontal axis are possible threshold values for tau. Along the vertical axis is the Gini gain computed from the formula. Every point on the curve represents one candidate rule, one pair of leaves, and one weighted impurity reduction. The demonstrated split near 8.5 minutes has a gain around 0.20, so it is a useful split. But the curve also shows that a nearby threshold does a little better, with a best gain around 0.219. That difference is the reason algorithms search systematically. They are not looking for a threshold that merely seems plausible. They are looking for the threshold that maximizes the scoring rule. Now the threshold sweeps across the feature range while the marker moves along the gain curve. This connects the picture of the split to the numerical score. When tau moves, sessions switch leaves. That changes coverage, class mix, Gini impurity, weighted after split impurity, and finally gain. The curve is just all of those recalculations lined up from left to right. The sweep ends near 8.8 minutes, slightly different from the earlier 8.5-minute example. The lesson is not that 8.8 is a universal rule for websites. It is the best threshold for this sample, this feature, this target, and this impurity criterion. A decision stump chooses the threshold with the highest gain because that split removes the most weighted impurity from the parent node. Let's recap the workflow. We began with labeled website sessions. Each example had a time value and a purchase outcome. We sorted the sessions by time so candidate thresholds could be tested. For any chosen tau, the stump sent x less than tau to the left leaf and everything else to the right leaf. Then we evaluated the leaves. We looked at outcome mix, coverage, and Gini impurity. Lower Gini meant a leaf was less mixed. To score the split, we compared the parent impurity with the weighted impurity remaining in the two leaves. The threshold with the largest reduction became the selected split. A larger decision tree repeats this idea. At each node, it considers candidate splits, scores the impurity reduction, chooses a strong split, and then continues growing on the child nodes. If this lesson helped, please like and subscribe, and visit the website to try the live interactive widget where you can move the threshold yourself.